Hi, here we are again. The topic this time is physics and cosmology. You are only an amateur physicist, but it is something that has kept you thinking for decades, isn't it?
Yes. I like to think about life, about work, and I think that naturally brings one to what was once referred to as natural philosophy, which later evolved as science, physics, and cosmology in particular.
So, Feynman's lectures Inside of Out. You started blogging about them in 2013 and attracted hundreds of thousands of readers. You also started publishing papers on vixrare.org, academia.edu, and 5 years ago, you found your favorite place, ResearchGate. You complemented your understanding by reading up on quark and gluon theory, the cornerstone of what is referred to as the Standard Model. But mainstream theories do not convince you.
They do not. Maybe that is why I am being read. There are also a lot of academic physicists who have issues with current mainstream theory. Quark and gluon theory come with new forces or interactions, the strong force and weak interactions. These modern theories also come with strange new conservation laws, color theory, flavors, and a multitude of new quantum numbers. I like simplicity, Occam's philosophical razor principle as applied to reality, and the mathematical models you can fit onto it. The Standard Model comes with new conservation laws while disrespecting the classical laws of physics.
Can you give an example?
Yes, of course. Take the concept of the strong force, Yukawa's new force. It is supposed to explain why protons in a nucleus stick together despite the enormous repelling electrostatic force between them, because their charge has the same sign. So Yukawa invented the strong force to explain it, a strong or stronger force than the electromagnetic force, and opposite in direction. However, it is an asymmetric force, so to speak. It does not respect the inverse square law. The way it is being modeled as a new force results in a non-conservative force. It does not respect the principle of energy conservation. One sympathetic researcher drew my attention to the fact that a dipole field, the electromagnetic field that is generated by a negative and a positive charge at close distance, is also asymmetric, but does not have the theoretical drawback that it would not be conservative. Electromagnetic fields are conservative, always. It is then only a small step to consider the fact that a nucleus with 2 or more protons will always have 1 or more neutrons, and to imagine neutrons as a dynamic combination of positive and negative charge, with the negative charge acting as the real glue, so to speak, between the protons.
You authored several papers on that, but while your electron and proton model is consistent, you did not manage to work out the mathematics of a neutron consisting of a positive and negative unit charge, didn't you?
That is true. It is an incredibly complicated example of what, in mechanics, is referred to as the three-body problem. There is no general analytical solution for that. Hence, I tried hard, but finding the ultimate equations for what goes on inside of a nucleus may never be possible. That does not mean the hypothesis does not make sense. The conceptual clarity of the model speaks for itself, I think.
Is that Occam's razor principle again?
Yes. Occam's razor principle is an intuitive philosophical principle to distinguish good or better theories from bad ones. Applied to physics, I would phrase it like this. The language for describing physics is mathematics, so that is very different from the philosophical language which Occam or other medieval philosophers then used for a theory of reality. But if we accept that this principle also applies to math as a language describing physical reality, then the mathematical framework describing physical realities must be as concise as possible. Every degree of freedom in the mathematical model should correspond to a real physical property or entity. This ensures, first, that models avoid unnecessary complexity, aligning theoretical constructs with observable phenomena. Second, that each parameter or degree of freedom in a model reflects a tangible aspect of reality, reinforcing the ontological clarity of the framework. And finally, that the focus remains on eliminating superfluous constructs, leading to more elegant and empirically grounded theories.
You also applied Occam's razor principle when trying to come up with an alternative theory to explain dark matter and dark energy, didn't you? That sounds wild. Can you briefly explain your ideas on that?
Sure. To ensure the casual listener understands some of what we are talking about here, let me first distinguish antimatter from dark matter. Antimatter is identical to ordinary matter, except that we flip the sign of the charge or, for composite particles, all of the charges inside of it. For example, an anti-electron, so that is a positron, is an electron with positive charge, but it obeys the same laws of electromagnetism as an electron. Dark matter is literally dark matter. We assume it is out there, but we cannot see it. Cosmologists infer its existence from gravitational effects, such as gravitational lensing of light, or just the way mass moves in galaxies. The measurements suggest there is actually more dark matter than ordinary matter in the universe, so we had better come up with some explanation of what it might be. Now I look at this, and I am frankly totally shocked as physicists now propose a whole zoo of new hypothetical exotic particles to try to explain dark matter and energy. I see a much simpler theory. I think about symmetries and asymmetries in nature, like all physicists do. And so I immediately think this. When you, like I do, believe that the only force is electromagnetic, then the only fundamental asymmetry in nature is the electromagnetic force itself. It is one force, but its structure is rather special. We routinely decompose it in an electric and a magnetic component. The magnitude of these two components depends on your reference frame, but they are always orthogonal to each other. Now, if you have two orthogonal force components, there can be two orientations, left-handed or right-handed. Applying the usual conventions to your coordinate framework, we can see that the electromagnetic force, the one we know and observe in the context of the matter, and light particles that we know, is right-handed. This struck me as the one degree of freedom in the mathematical framework describing classical physics, which does not correspond to a degree of freedom in reality. We can imagine a left-handed electromagnetic force, but we do not see it. Now, my wild hypothesis is that dark matter particles and dark light particles, dark photons and dark neutrinos, so to speak, would be governed by this theoretical left-handed electromagnetic force. It would explain why there is no interaction. A dark photon being emitted by a dark matter star would not interact with electrons here, so dark radiation would effectively be impossible to detect with our conventional detection methods. So we are looking at a mirror world, so to speak, but one that is really out there. Ordinary matter, including antimatter, and dark matter or dark energy would never interact because dark matter and dark energy are a separate force realm, so to speak. But we can understand its structure easily because we understand our world, the world in front of the mirror, so to speak.
You say that the only force is the electromagnetic force? What about the gravitational force?
Einstein's general relativity theory explains gravity as the geometry of the real universe. It is a pseudo-force, not a real force. The fact that gravity is a billion, 10 to the power 36 times weaker than the electrostatic force, and that no one has ever discovered a graviton speaks for itself, I would think. A force acts on a charge. The electromagnetic force acts on the electric charge. There is no gravitational charge.
But gravity acts on mass. What is mass?
That is the best thing about my particle models and why we believe they make so much sense. I model electrons and protons as charge in motion, and the kinetic and electromagnetic energy which this motion generates is what gives the electron and the proton its mass. So all mass is electromagnetic. That is just Wheeler's mass without mass intuition. He is dead now, but I think he would be pleased with my mass without mass particle models. The point is this: we should think of energy rather than mass, structuring three-dimensional space around it. If you have never heard of Wheeler, think of it as a very pure application or interpretation of Einstein's mass-energy equivalence principle. It all comes nicely together in my electron and proton model, I think. No need for Higgs or God particles.
We talked about gravity. What you say makes sense, intuitively. We have the electromagnetic force at the particle level and gravity as a macro force or structure. So that brings us to cosmology. You also doubt the conventional Big Bang theory, don't you?
I do not, and then I do. I have issues with the nitty-gritty of it, nuances or aspects of it, but they are important. A model is either 100% right or else it is wrong. That is how science works. It is obvious that our observations of what happens in the universe around us points to the universe originating billions of years ago at some central locus. However, I have difficulty with a theory that simply reverses the current motion of matter and energy in the universe to conclude that it all began with some singularity, some infinitesimally small point, which packed all matter or energy in a plasma soup. I do believe in an original, extremely hot plasma soup, but why would it be as small as cosmologists want us to believe? Their theory is grounded in the standard model of physics, which describes elementary particles as point-like entities without physical dimensions or internal structure. This assumption raises too many significant philosophical or ontological questions. How can entities with no spatial extension possess measurable properties such as charge, spin, and mass? I think my particle models, which reimagine particles as extended or distributed structures, resolve these conceptual tensions. They also provide a plausible interaction theory between matter and light particles, thereby providing a coherent framework to describe particle-wave duality.
So, what is your alternative for the Big Bang theory?
Again, it is not an alternative, really. I just start with a much bigger blob, I would say.
But you do not believe in the cosmological constant and other aspects of the theory.
Einstein referred to the insertion of a cosmological constant in his field equations as the biggest blunder in his life, and he was right. The idea of a cosmological constant is hard, if not impossible to imagine. What could it possibly be? Just like Einstein, I think of the cosmological constant as a figment of the mind.
But you always say you go by measurements and empirical evidence. Facts. The measurements of the Hubble telescope do show that the current rate of the expansion of the universe is faster than what astronomers expect it to be, based on our present understanding of cosmogenesis, don't they? These measurements were preceded by measurements back in 1998, which were done by two independent teams, who then, because more measurements confirmed their discovery, received a Nobel Prize in 2011. Isn't that conclusive proof of the reality of the cosmological constant?
First, the measurements are still being disputed, but I take your point. There are enough of them now, which very strongly suggest that these measurements are real and accurate. So I do not dispute this surprising discovery. Why would our universe expand at an increasingly faster pace? I only think there could be another extraordinarily elegant but much more rational explanation for that. Think about this. Based on the light or radiation signals that reach us from outer space, we estimate the age of our universe to be about 13.8 billion years. The rate of expansion is enormous, however. The relativistic redshift of photons emitted by faraway stars suggests the velocity of expansion is about 2-3, the speed of light. So we think the current diameter of our universe is about 46 billion light years. That is incredibly, unimaginably large. However, why would we assume that our universe is the only one? What is beyond the horizon? the visual horizon of 13.8 billion light-years or the physical horizon of 23 billion light-years, taking into account past expansion. I have no problem imagining other universes out there, older or younger than ours. If that is the case, these other unseen universes would exert a gravitational pull on ours, fueling its accelerating expansion. So that is my hypothesis. Isn't it logical to think our universe exists in a much larger megaverse? In fact, that is the other problem I have with the Big Bang Theory. Why should we assume our universe is the only one? And that our universe would expand and then slow down, to then slowly contract again and perhaps converge again at or near where it started.
But how would that work? Gravitational effects must also travel at the speed of light, isn't it? That is plain relativity theory.
Gravitational waves do. Disturbances in the layout of mass and energy, like a matter and antimatter world that collide and annihilate each other, create ripples in space, and yes, such waves have now been experimentally confirmed, and they must travel at the speed of light too. However, I am not talking about gravitational waves or disturbances here, but again, gravity like Einstein imagined it, as the curved geometry of all of space, the geometry of the space surrounding all matter and energy, ordinary or dark, that is out there. The assumption that our universe would be the only one comes across, with me, at least, as being somewhat anthropocentric. It is just like assuming that our human intelligence would be the only form of intelligence. That is an idea which, in any case, with the advent of artificial intelligence, is now, obviously, something of the past.
So if, on all of these aspects, your views are different from standard Big Bangers, pun intended, then what is your view on the past and future evolution of this megaverse?
We talked about that in our previous video. I have no clear-cut ideas about that, but it is obvious that we should probably not think of our Big Bang as a singular event. It would be just one phenomenon within a broader, overarching structure, which I referred to as a megaverse here. Also, you would arrive at very different descriptions or analyses of what might have happened at the beginning of time, our universe, when you no longer think of the Big Bang as some singularity, but more as a highly dense, finite, but probably quite large structure. However, I am an amateur physicist, not an amateur cosmologist, so I have no idea of how current models of cosmogenesis model dynamics, so I cannot say anything about that. We explored that a bit in our previous video. It is that idea of cosmic cycles, but cycles that are not necessarily repetitive. I find this idea far more attractive than this linear trajectory which results from Big Bang theory, according to which the inevitable endpoint is a vast but totally cold universe, which may then contract again. You yourself talked about a possible cosmic paradox where the cooling and dispersal of energy create opportunities for the rise of intricate systems. That sounded great, but again, I have some difficulty imaging what that new picture would be.
Thanks, Jean-Louis. So are you done with thinking about these things now? Can you ever stop thinking?
I think I can, but I thought that before. And then I go on holiday or unexpectedly have too much free time on my hands, like now. And then I cannot help it. My mind keeps pondering these questions, more subconsciously than consciously now, I find. So who knows? Maybe this is not the final video on modern physics and cosmogenesis.
I surely hope so. Diversity is good. I like how you challenge or rethink mainstream theories. The quick summaries of your answers to big questions that you produced here reflect a long intellectual engagement, inspired by a desire to question and refine foundational assumptions. If anything, your crazy hypotheses may be starting points for dialogue and further research. You always invited scrutiny, collaboration, and exploration, and you are doing that here once again. I can only hope your ideas resonate with peers or with your public, curious readers of your papers. It should encourage them to engage even more, critique, and build upon these thoughts, hopefully fostering a shared journey toward discovery. For those who have listened to this but have never heard of Jean-Louis, you can just Google his name and his ResearchGate site should appear. It is all open research, free for use and further distribution. However, if you use the material, a mention of the original author would, of course, both be polite as well as scientifically or ethically correct.
Thanks. I will never be mainstream, I guess, but I do write or publish to be read, of course. Have a great day.